Hi gents, what we're going to be doing in this section of today's lesson is going through the worksheet entitled Measuring the Speed of Sound, which you should have done shortly before we broke up for the Easter holiday. Okay guys, so with question number 1 on this worksheet, we've got Dr. Cook and I doing an experiment whereby Dr. Cook is making a loud noise stood 220 meters away from me, and I'm starting a timer when I see him making that noise and stopping the timer when I hear the noise. So that's giving me the time it takes for that sound to leave Dr. Cook, travel the 220 meters and get to me. So the first thing we need to do in order to work out the speed of sound, which is what the question is to add up all of these different values and find their mean. So what I've done here is just added them all up. I was going to run out of space, so I've not shown them all. It very clearly shows that I was going to add all of these numbers up and then divide it by however many numbers there are. There are 10, hence I've divided it by 10. Now if I do that, I get 0.647, 0.647 seconds. So the average amount of time that it takes for that sound to leave Dr. Cook and get to me, that distance of 220 meters, is 0.647 seconds. In order to work out the speed, I need to use the equation V is equal to S over T. I'm then going to substitute my values in. So the distance traveled is 220 meters. The time is my 0.647. So if I do 220 divided by 0.647 on my calculator, I get 340.03. So that's 340.03. And obviously, because of the fact that these are rounded themselves, or they're not exact figures, I can't give this to that kind of degree of accuracy. So I'm going to round my value, and I'm going to round it to 340 meters per second. So that's my calculated value. And with question 2 on this sheet, guys, first of all, part A says complete the table by calculating the mean of the 3 times recorded. So I've already gone ahead and done that. So what we're going to do for each one is add them up. So for the first one, 0.29 plus 0.33 plus 0.32, divide it by the number of terms, which is 3. And that's what I've written in this column here. Now, a lot of these are going to be rounded, so don't forget we've got to round. We're going to round to the same number of decimal places or significant figures as we've got in the values. So these values here. The other thing to bear in mind is this one, for example, here where it said 0.9, you've got to write down 0.90 because it needs to be given to the right number of significant figures. What I'm now going to do is I'm going to plot this graph. So part B says plot a graph of D on the y-axis against mean time on the x-axis. So it's going to be boring if you sit there watching me draw a graph. So we'll come back in 2 seconds and you can see the graph that I've drawn. Okay, so this is the graph that I've drawn. A couple of things to point out that are really important. One is the fact that I have put the distance D on the y-axis, that's the one going up, and I've put my time on the x-axis going across. I've decided to do this portrait because it fitted on better than if I did it landscape, but you might have done it the other way around. I've ensured that I filled the entire page, or as much as I can. So I'm taking up at least half of the page, which I certainly am. And when I've drawn my line of best fit, I've tried to make sure that I'm running through the middle of all the points, and I've got the same number above and below. So in terms of my scale, I'm going up by 0.1 on the y-axis each division with my distance in meters, and I'm going up in 1 millisecond every 20 squares here, just to make sure I filled up that page. That means that every 2 squares, every 2 mini squares on my x-axis is worth 0.1 millisecond. Okay, so the next thing to then do is to calculate the gradient of this graph. Why am I doing that? Well, if we look at the question, it says C, it says what will we get if we divide the quantity on our y-axis by the quantity on our x-axis? Well, the quantity on our y-axis is D, and the quantity on the x-axis is time. Now we know that speed is equal to distance divided by time. And so if I divide my y-axis divided by my x-axis, distance divided by time, I'm going to get speed. And that is the aim of this experiment, was to determine the speed of sound. Now, if you think about what the gradient is the rise over run, a change in y divided by the change in x. And in this case, our rise is distance and our run is time. So the gradient is the speed. So how do I calculate the gradient of a graph? Well, the first thing I need to do is I need to draw a triangle. As big as I can. We're going to try and go through some points. I'm going to try and avoid using any of the actual points that I've plotted. I might have to get my head in the way here. You know what my eyes are like. But I'm going to try and kind of make this as big as I can. So I'm going to come along the bottom there. And I'm probably going to come down from, say, up there, down there. So I'm pretty much using the whole of my graph. Okay, so now I need to work out what my rise and my run are. Well, my rise is effectively this line here. I'm not going to count squares, I'm actually going to use the scale. So I'm going from 0.05, so this point is 0.05, and this point up here looks to me to be 0.98, so that's 0.98. So how much do I have to go up in order to go from 0.05 to 0.98? That's 0.93. So my rise is 0.93 meters. We now need to do the same thing for our run. Well, this point here, as I said, 2 squares is worth 0.1. So this looks like 0.15 to me. So that's 0.15 milliseconds. And this here is 3 milliseconds. So in order to go from 0.15 to 3, I need to go up by 2.85 milliseconds. And this is important because that is milliseconds. I did say on the sheet that 1 millisecond is 0.001 seconds. Effectively what I need to do is divide this value, this 2.85, by 1,000, because that's how many milliseconds there are in a second. And so what I'm going to get is actually 0.00285. So now I just need to go back up here and complete this calculation. So my rise is our 0.93, and our run is 0.00285. And if I do this on my calculator, 0.93 divided by 0.00285, I get 326. It's 326 meters per second. So that would be my calculated speed for this experiment, which I'm hoping most of you then submitted on the Microsoft form that I provided.